What is the kernel of a matrix? Watch out. This name here is also called null space. Sometimes people call it null space. Okay, this is a synonym. Those are synonyms. Okay, null space if you like this kind of name, or kernel if you like this one. I call it kernel. Okay. So, kernel of A, all the x's in the domain such that in the codomain I go into 0. Let's make an example. I have domain, let's make it in this way, domain and codomain. And then I have how many AIs will I have in this case? Gus. How many AIs will I have? I go from 3 to 2. How many EIs do I have? I got E1, E2, E3. True? That means I will have A1, A2, A3. True? Perfect. Let's pretend that I have this one. A1, A2, A3. Now, this A2 is double A1. If I take -2, 1, 0 in the domain, that means -2, 1, 0, this point here, this x here, where will it be? Discuss. If I write with the same one, do you see? Well, I move to the same one. So I was thinking it was not visible. People, what would you say? 0, true? 0. We are together that it's 0. Perfect. If I take, let's see if you see it. If I take half x, 0.5x, is this a linear transformation? Yes. Did we compute a cause-effect relation? Yes. Cause-effect. True? If I take half a cause, I will have what? Half the effect. True? So if I take 0.5x, I'm going to go into 0 again. True? You see it? And if I take minus 12x, this is a cause. That is minus 12 times a cause. The effect is going to be minus 12 times that effect. Minus 12 times 0 is going to be perfect. All this stuff here goes mapped into this. We are together, people, true? Kernel of A. All the stuff in the domain that in the codomain gets squished into 0. True? Watch out. Do we need square matrices to have a kernel? Do we need m equals to n to have the kernel concept? Yes, no, I do not know. Very much no. You see the example that we go from R3 to R2. Okay? So this is a very common misconception. But of course, in automatic control, this stuff here is going to be specialized for square matrices, and it will have a very special meaning. Let's see if you see it. Okay, so geometrically, domain, codomain, we have the calligraphic A. We have the possibility that all the domain, typically the domain is going to go into the range, true? And the range might be a subspace of the codomain. Are we together on this drawing? The kernel of A is going to be a subspace here that goes here. Okay? Perfect. So we might have that the kernel is just 0 because only 0 goes into 0. Let's make an example. 1 minus 2, 1, 0.37. For this matrix here, the unique point that goes into 0 in the codomain is going to be 0 in the domain. We might have this situation here. We might have that all the domain goes into the codomain. All the domain is a kernel. Example, A equals to 0, 0, 0, 0, 0, 0. Here, all the stuff in the domain goes into the kernel. Is the kernel. The kernel is in the domain. Watch out. The kernel is in the domain. Are we together? So, kernel is in the domain, range is in the codomain. Okay? How much are we together up to now, people? Before I continue, ignore this for now. Yep.
To have the concept of kernel different than 0, so that is something. Is it related somehow to have like linearly dependent A? Or we could have a kernel different than 0 also if all the A's are not linearly dependent.
The second. And then we do it, I take some draw. Okay, let's do it this way. Domain that is two-dimensional. Let me think. Got to think. I've got to think in terms of rank nullity theorem that we didn't do it yet. So do we need rank deficiency? I'm thinking of the cases. So the case for which we have a bigger domain, they will be linearly dependent. So in this case, for sure, we are going to have a kernel that is non-null, and the issue is you don't have all the tools for now. You don't have all the tools. Let's arrive the rank nullity theorem, and then we are going to discuss this. Okay. So it's better that we do it there, because otherwise I inject something that I don't want to inject right now. But it's going to be answered whenever we do the rank nullity theorem. Okay. So ignore this thingy here up to now, the last 2 minutes, and then let's go here. How do we compute the kernel? What do we have? Ignore this drawing here. We need to have Ax equals to 0, true? The x's that satisfy this are in the kernel. So the kernel is somewhere here for which the x's are equal to 0. That means x1, x2 equals to 0, 0. That means that whenever I take this times this, I need 0. True? That means that this vector and this vector are orthogonal. True? Are we together? X is in the domain. The rows are going to be in the domain. And for example, for this specific A, this row here is going to be minus 1, 1. This is my T1. Let's call it T. And the second one is going to be T2. Are we together up to now? Now, which vectors in the domain are going to be orthogonal to both of those ones? Well, this one, is it going to be orthogonal? No. This one, sorry, is it going to be orthogonal? Yes. If I take this inner product of this, I get 0, and this inner product of this, I get 0. Do you see it? Do the computations. Read this, think at this. Very much together, not at all, kind of. I see people writing, I do not know what you are writing. What is the codomain? R2. What is the range? A1, A2. Do you see A1, A2? Look, the codomain is R2. The range is R1. We have rank deficiency. Indeed, what do we have? We have determinant equal to 0, true. Determinant of this stuff is equal to 0, perfect. Very interesting. We have T1, T2. If we take all the stuff here, we go into here. And this is very interesting. So if I take this, I go here. If I take this, I go here, true. If I take these, if I take these, I go here, true. If I take this one, this object here is this one minus this one. It's this one minus a little bit this one. True? Are we together? Do you see it? I put numbers. Sorry. I'm kind of messing up. This goes into this because it's obvious. So this is point 1. Then we have point 2, that is this one goes into this one, and it's my point 2. Then I have point 3, that is 2 plus this one, true? Point 4. Are we together? Point 4 goes mapped into 0, true? Point 3 is the sum of this plus this. Sum of the causes will mean sum of the effects, true? Point 3 is going to be here too. Do you see it? Eventually, all the points along these, that is, all the points that are parallel to the kernel, will be all mapped into this point. This line here is going to be mapped here. This line here is going to be mapped here, etc., etc., etc. And you see how those parallel lines to the kernel, in a certain sense, go, each of them, squished into one specific point. And indeed, the whole kernel is what? It's the stuff that goes squished into 0. There was a question there, I think.
I'm not sure how to formulate it, but is the kernel only defined for matrices with rank 1?
No, what?
Or kind of what I'm saying is, because if you multiply A with X, right, you get 2 equations. And if you essentially have 2 different conditions defined by those equations, they can't be solved to get 0, right? Maybe the first thing I said about rank is nothing, but at least that's I'm curious about.
How do I compute? make it like this way. Let's make it this way. -4, -6. How do I, this is from R3 to R3, true? How do I compute the x's that get mapped into 0? I look at this one that is orthogonal to this, and this simultaneously, true? Do you see that those three that I'm drawing, they are aligned, true? So if I've got in R3 a certain vector and it's this one, what is orthogonal to this vector? It's going to be a plane, true? All those vectors here in this plane that are orthogonal to this vector here, blue vector, are going to be mapped into 0, or better, 0 here, true? But then I've got, this is the opposite, but the same is orthogonal. This is twice, and the same is orthogonal, you see? So all the stuff that is in this plane is going to be mapped into 0. See it? Now, from a geometrical perspective, do you see that if I take this plane here, it's going to be mapped somewhere else? True? Because, let me do it just a moment. If I take this point here, this vector here, this vector orange here that is in this orange plane is going to be what? It's going to be essentially something that is in the kernel plus something that is outside of the kernel that is aligned with the first one. You see it? So, do you see it, people? I should do it a little bit bigger. I do it in a different page because this is an important. Are we together that I have this one? This is my T1. Then I've got T2 and T3 that are aligned together. Then I have, and I'm working in the domain here, I've got all the stuff that goes mapped into 0. Together? It means this point, this point, this point, this point, this point. This one that is 0 in the domain, I knew that it was going to go 0 in the codomain. But since I'm constructing T1, T2, T3 that are the rows, this one also is orthogonal because it's this stuff here and it's orthogonal to all the T's. This one too is going to be into here. We are together. True? People follow me. This is an important representation. Follow me from a graphical perspective because this is unlocking the intuition of the kernel. How much are we together up to now? 1, 2, 3. Perfect. If I take now this vector here, let's call it x bar. X bar is going to be equal to x, let's call it tilde, plus something, let's call it x happy. Now, y bar is going to be y happy plus y tilde. True? Are we together? This is linearity. Because x bar is sum of causes, y bar is sum of effects. We are together. We already know that this one is going to be 0. Why? Because in a certain sense, this x tilde is in the kernel. We know it goes mapped there. And if I was taking not only x bar, but x bar moved, x double bar, that was something here in the kernel plus the same x happy, y double bar would still be y happy, because it would be y happy plus something that goes into 0. You see? You see? That means that the whole plane where is basically I'm lifting the grid, the red plane, I'm lifting it up to here. All this plane is going to go into y happy. 1, 2, 3. Let's redo it here. Let's redo it here, that we have the numbers and we see it better. If I take this point here, or better, let's make it this way. This one, this x, where does it go? It goes in 1a1, true, plus 2a2. We go here eventually, true. Do we see it? If I was taking this one, would have been more interesting. This one goes into here, I think. Are we together on this? 1, 2, 3. Because I'm taking 1a1 plus 3a2. Perfect. If now I move in this direction, it's like taking this object plus something along here. True? So this whole stuff here is this plus stuff that is here. And that means any x, if we call this x bar, and this is my y bar, any x tilde that is along this plane is going to be x bar plus x kernel, let's call it in this way. All the x kernels, they go into 0. The y tilde, they are still going to be y bar, because they are going to be y bar plus 0 because the x kernel goes into 0. Okay? And if I take now this one, let's see. If this whole line passing through those points here go here. If I take this one, where does it go? This whole map, this whole line, where does it go? You tell me. You tell me. People, what would you say? Where do we go? How many of you agree with me that we go here? I agree. Do not agree at all. No, do not agree. I do not know whether to agree or not. So this cause creates this effect. This one is half the cause, true? We go into half of the effect. True? Let's see it. Are we together that this whole line is going to go mapped into one point? Are we together that that whole map line is going to be into one point? Perfect. Let's take one of the representatives of the class and let's see where it goes. If I take y of this x, it's going to be twice a1. No, sorry. Sorry, people, I messed up with a1 and a2. Okay. So, but you got the point, though. So I messed up with a1 and a2. but I think you got the point. Okay. Sorry, my mistake. Let's see. We are very much together, not at all, kind of, to do a little bit of damage control. Are there questions? Because this one is twice A1 and once A2. And in my vision, I was looking at this one as A1, so I was counting twice A1 minus A2. Okay? But actually, given those numbers, it's twice A1 minus A2. So it would go, this point goes here. With the right notation, this point goes here. And actually, this doesn't go here, but goes down. See? So, but I think you got the point, true? Excellent. Do. Go. You do. 14. Oops. Go. Do drawings. Drawings. Ah, signore. Okay, people, I don't know if we obtain the same information. I hope we get it. So we start from R2 and we go into R3. We have A1, A2. Then we have T1, T2, T3. That means the kernel is orthogonal to the stuff, and the range is this space here. That is the span of the columns. If I take anything here we go into this. If we take any line here, it's going to be mapped into some point somewhere. If I take, for example, I don't know, E1, if I take this point here, should go into A1. If this one is A1, if this one is E1, sorry, if this one is E1, all this stuff here goes here. If this one is twice E1, this one goes into twice A1, etc. You see? Okay. Together, not at all, kind of. I see some twos. Why two? Which question do you have, people? Range is the range is in the codomain. Here we start domain 2-dimensional, codomain 3-dimensional. True. So the kernel is in the domain, so it's something that lives in a 2-dimensional space, and it's this subspace here. The range is a 1-dimensional thingy because we have a 1-dimensional span that is in the codomain.
And it has all three axes they are, or like.
I didn't get the question. Sorry. In the codomain.
Yeah, in the codomain. The values that can be have or like a part of every axis.
It's a line aligned. This one, the range of A in the codomain is something that is spanned by those two vectors, that is essentially spanned by this vector. So every line in the domain is going to be a fraction or a alpha times 1 to 3. Other questions, people? Let's go on. What would you say? I would hope that everybody says square because we are interested in this stuff here. True. Excellent. And in square matrices, we see everything. We have A, that is A1, A2, and this one tells me the range. And then I have T1, T2, and this tells me the kernel of A, true? So I see everything. I see that this stuff here goes, let's see. Can we have convergence? For this matrix here, can we have that the origin is a convergent equilibrium? Let's see if you see it. What does it mean that is a convergent equilibrium? It means that starting somewhere else, I go back. True? If I start in the kernel of A, my x dot is going to be equal to 0. Can I have convergence whenever I've got this stuff here? No. You see it? Perfect. We are going to do this thing here. Anyway, let's go back to a visualization. Look at this 1 minute and tell me if we are together. Somewhere else from the equilibrium. That's all the initial conditions are delta. Delta will be This direct duality theorem that don't works for general matrices that we're going to see very soon. It's the answer to the question that you were asking before. If we arrive there today. People, what do you say? What do you say? You see, you visualize things. Perfect. Very interesting part. Whenever A is symmetric, we have something that is very, very, very interesting. The kernel is going to be orthogonal to the range. This is a very valuable thing in machine learning. Anyway, we don't delve into this topic here. For people that are interested and will meet symmetric matrices, remember this property. It's very interesting. And here, the kernel is equal to only the origin. See? In general, whenever we will have T1, T2, that they are spanning everything, whenever we will have that the determinant is different from 0, we will have eventually something that is, sorry, the determinant equal to 0, but we do it later. I kind of keep going back to the rank nullity theorem in a wrong way because we didn't do it yet. Anyway, here you see that the kernel is 0. The element 0. Are we together? Because there's no vector that is simultaneously orthogonal to the stuff here, but 0. So we are going to say that a matrix A has a trivial kernel whenever the kernel is only 0. 0 is always in the kernel because 0 gets mapped into 0. 0 of the domain goes always into 0 of the codomain. So 0 of the domain is always part of the kernel. The kernel cannot be an empty set. Symbol for empty set. Kernel is at least the element 0 of the domain. Whenever this happens, we say that A has a trivial kernel. Are we together? Perfect. Let's ignore it. Let's go back to the main question that we were having before. Let's assume that the kernel of A has dimension bigger than 0. That means in the domain, all this line goes mapped into, in the codomain, into 0. That means if I have x0, that is my initial condition here, or 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 here, and I write this autonomous system, do I move? No, I stay there. You see? Let's go back here. This one is a situation for which if I start here, 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 or here, what happens? I stay there. So, can the origin be convergent? No, because to be convergent, there must be a delta around the origin such that starting anywhere within this delta, I will eventually converge back. True? This one, if I start there, I stay there. It can't be convergent. Necessary condition for having convergence in linear time invariant system is that the kernel is trivial at this point. Okay? Okay? How much are we together, people? Okay. This one you do at home. Bigger matrices you do at home. Let's do this one. People will do the same. I would like to see the answers, everybody, people. Everybody, please. What would you say? Table there. For sure cannot be asymptotically stable because asymptotically stable means convergence plus marginal stability. Whenever I have kernel of A that basically any neighborhood of 0 will contain some equilibrium, I can't have convergence. So that means I can't have asymptotical stability. Tomorrow we continue and we see things. There's a question actually before.
Just wondering about asymptotic equilibria that are in the origin. But couldn't you say that
We are going to do it tomorrow because I think it's 4. But tomorrow we start with a question. It is a very interesting question. If I have x dot is equal ax, think at home about it. Can I have asymptotically convergent, asymptotically stable equilibria that are different from 0? Think about it. May, in this case here, we have equilibria that are not 0, that are asymptotically stable. Think about it. Let's see if tomorrow you will have answered. Is the question clear? Can I have this point here, x1, x2, for this situation here, this one is asymptotically stable? Think about it. Tomorrow we see.